All right. You have already heard the first part, which is presented by Fabian about the standards comparisons. And now I'm going to give you a brief overview about the specific application within this very niche field of products. So I'm going to present an overview about the use or the application of vacuum generator circuit breaker in, or let's say, for synchronous condenser applications. So we will start with the part where I give you, let's say, about some info, some insights about why to use a synchronous condenser, what is the idea behind using these applications. And secondly, we would go into details about which kind of let's say requirements a GCB has to face when dealing with synchronous condenser. And last but not least, I'm going to give you some info what we have done in few feasibility studies with our vacuum generator circuit breaker, especially for synchronous condenser applications. So let's start with a brief overview about the, let's say, the application field where you would use vacuum generator circuit breakers. So I think it is already a well-known fact that vacuum switching media is widely used in the medium voltage for the last 40-50 years. And especially vacuum generator circuit breakers are used actually at the moment mainly in the conventional power generation. You can find that in conventional power plants, hydro pump storage, depending on what is the rating and depending on what the requirements about the switching numbers, which is required from the power plant itself. We have at the moment in the field around about almost 4,000 GCB units, which has been installed. So actually a quite great installed base with our Siemens vacuum generator circuit breaker, mainly in power generation. A small part of that are being used in oil and gas applications. And then a little bit, let's say, larger portion of that are being used into utilities and industries. So beside the arc furnace and data center applications, of course, you can find the synchronous condenser applications, which, let's say, is being protected with the vacuum generator circuit breaker. So what is the reason behind using synchronous condenser? The challenges what we are having right now in the power grid is the trend is going into reducing the use of nuclear and fossil power of power plants, which is ongoing. And because of that reason, there is a lack of short circuit power, of course, in the grid, which can cause stability problems in the high voltage grid. And in addition to that, of course, when you reduce the use of nuclear power or a different kind of power, you need to find kind of alternatives, and that's why the renewables power plants or power generations come into the question, such as PV and of course wind power, which can cause, of course, stress to the power grid. The next, let's say, factor which contribute to this grid problem or grid challenges is that the international transit trade of electricity is growing. So that might cause, let's say, further stress and burden for the transmission network. So all of these challenges are resulting into problems that, as I mentioned before, we might have a problem with the lack of short circuit power in the grid. And those kind of problems will lead to voltage and frequency instability in form of swings in the grid. And of course, by reducing the use of certain power plant types, you will not have, let's say, a great number of generators which can produce reactive power, which leads to some difficulty when coming into power factor regulations. So all of these challenges and problems, let's say, ask for the use of, asked for a solution how to solve these kind of problems. So there are different solutions right now in the market dealing with these kind of problems. For example, of course, you can use synchronous condenser. You can use let's say, transformer combination to solve these kind of power factor regulations. And also there are different kind of capacitor banks to solve these kind of power factor issue. However, it has been established that using synchronous condenser has been widely used. Of course, the reason behind that is mainly because the solution is quite flexible in regulating the power factor. And the second point is, of course, using synchronous machines to regulate power. You can also provide the network with the short circuit power, which is actually missing here and which we have identified as challenge. All right, so we just have a glimpse about why is this important, or what is the application field of using synchronous condenser. But as you guys remember that this webinar is about GCB, so I would like to jump into the next slide, talking about when using synchronous condenser, what are the challenges a GCB is facing. So to show you that, I would like to use an example of a conventional power plant, because at the end, the main challenges for the GCB is similar whether you use that in conventional power plants or you can use this for a synchronous condenser. So as you can see, here is an example of how a combined cycle power plant looks like. To highlight right here is we have a generator circuit breaker, or GCB, is connecting the generator step-up transformer and the generator. Depending on the size of the power plant, that means the connection can be realized via isolated phase bus bar, it can be by normal bus bar or cable. And one point we can see right now is that the connection between generator and GCB is quite short. So because of that reason, you have, when it's translating into an electric network, we have a very highly inductive circuit in generator circuit or generator applications. So that means we might have a very short circuit current with high degree of asymmetry. Secondly is, of course, normal generator usually start with the power of 10 or even more megawatt. And we know for a fact that for synchronous condenser, the machine itself, even at the same power, they have very small short circuit reactances, which leads to very high short circuit current level. So that's for a fact, that's the challenge what the GCB has to face. And of course, depending on the power, GCB has to face a very high continuous operating current. You have listened to Fabian's session before, that depending on the machine type and machine parameters, a circuit breaker or GCB might have to face delayed current zeros. The reason for that, we will come to that in the next slides. And of course, as you can see, we have a very short connection between generator and GCB. That means the capacitance in the circuit is very small. And we just mentioned, or you just remember, we have a high inductance in the circuit because of inductivity like generator and transformer in the grid. And we have a very small capacitance, so which leads to a very high and steep transient recovery voltage when interrupting those kind of current. So all of these, let's say 5 challenges are challenging for a GCB to solve. And now I would like to go a little bit into the technical detail, how that come to the question. So these 2 terms you have seen before, we are dealing with generator circuit breaker. So that is why there is a standard which has presented by Fabian. So this standard introduce 2 terms. So we have to deal with system source short circuit current, and the other terms is generator source short circuit current. So let's start with the right hand side with the system source short circuit current. So basically, if a short circuit happens at the generator side of the GCB, then the current across the GCB will be fed by the system. The system means high voltage grid and transformer. So basically, every short circuit current is consisting of 2 components. We have the red part right here is the oscillating AC current, and you can see that it's normal. I think it's like the AC signal is very well known. And we have a constant amplitude of the current, which is fine. On the other hand side, you can see that there is an offset of the current, which is the direct current component. This current component is decaying, and this decaying of this direct current component is, let's say, determined by the grid X to R ratio. So I will come back right now to the question which has been asked in the chat. The IEC-IEEE standard mentioned that every generator circuit breaker has to be tested with the time constant of 133 milliseconds. So there's an equation where you can translate the time constant using the frequency of your network into the X to R ratio. And if I remember correctly, it would be an X to R ratio of 50 per unit. But we can calculate that later. All right, so that is about system source short circuit. As you can see, we have a constant AC and decaying DC components, but let's say at every time we always have a current zero. And just to remember, in the medium voltage, you need a current zero for the circuit breaker to clear the current, any kind of current, not only the short circuit. So the challenge for a circuit breaker for interrupting system source short circuit current is only that the DC component, that means this offset, is higher than in case of the distribution circuit breaker. Okay, we cover that part, and then let's go to the left-hand side. We have the generator source short circuit. As you can see, the breaker is the same. The set of generator and transformer is the same, but now the short circuit will happen at the transformer side of the GCB. So that's why the current across the circuit breaker right now is fed by the generator. And as you can see, we have two components, the AC component, which is oscillating, and the decaying component as a direct current component at the right-hand side. Generator itself is a highly inductive component, so that's why its DC component or armature time constant, which is written in the data sheet, is quite large. So that's why you have a very slow decaying behavior, what you can see here in this graph. And then secondly, generator itself, a synchronous generator, doesn't have only the main winding as a transformer. And depending on the design and depending on the manufacturer, you can have the, of course, the field winding, because we need an excitation for a synchronous machine. And then third, there might be a damping or damper winding, depending on how the design looks like. You might need that for stability, mechanical stability of the machine itself. So because of these three sets of different windings, in case of a short circuit, they will interact with each other in a transient process. And that's the result of that is that you can see here that the AC component decays as well. So if you would combine these two components, AC and DC, you might see a typical curve right here, that the short circuit current of the generator source fault can have delayed current zero. Delayed current zero means you don't have current zero to a certain extent. Okay, I cannot show that right now. And you remember, I just mentioned that in the medium voltage, any circuit breaker needs a current zero to interrupt those kind of current. So that asks for special requirements for GCB that besides having to deal with high DC components, around about 70 or let's say 60% DC, a generator circuit breaker has always to deal with delayed current zero issues. That means you have to test a circuit breaker for a certain long arcing time. So that is a specific requirements from the standard in which every generator circuit breaker has to fulfill. And then a third point, a third, let's say, task of the GCB. You have seen, of course, any circuit breaker of any sort has to be able to interrupt a short circuit current. We cover that with system source and generator source. But another task of the GCB is, of course, to synchronize the generator with the grid, because otherwise it doesn't make sense to have a generator. So basically, in the modern system right now, metering system, the possibility to have any kind of failure is quite low, because the system itself will detect what is the voltage level, what is the phase shifting between the generator and the grid. However, during maintenance, or let's say during installation, there might be wiring errors. So it can be that some service technician will, let's say, mistaking the two phases when connecting the wiring. So because of this reason, it might be possible that you will have false synchronization. And false synchronization means when you close a circuit breaker, a GCB, it will not, the generator and the network will not be in phase. So if that happens, you might have a typical curve of out of phase current, which looks like that. The rapid movement of the rotor inside the generator will cause this current constriction, what you can see here. So in such a case, when you open the circuit breaker, you can see that there is a very high offset, even though the current itself is very small. And that is, of course, a special requirement what a generator circuit breaker has to be tested for as well. And to that point we come to later, because we did cover that in our third part of this session with the simulation and feasibility study regarding this out of phase fault. All right, so we have talked about the characteristic of how short circuit current and out of phase current looks like when a short circuit happens in the synchronous machine, and of course especially in synchronous condenser. There is a standard existing explaining how to test the GCB, and of course the same standard does define as well what are the conditions to prove the suitability of a GCB in general. And this is this IEC IEEE standard which Fabian had explained in the previous session. So they clearly say what are the points, what you have to take into account when doing simulation. So that's the overview of that I'm going to give you right now. So we start with the fact that actually all generator applications, motor application in the medium voltage, they are operated with the isolated start point or with the highly impedance start point. And because of that reason, the maximum short circuit current level you can get is if a three-phase short circuit happens. And that is what we have to do when simulating short circuit, let's say when we're doing simulation, for simulation. Secondly is about what is the fault resistance when initiating the short circuit. We know for a fact that generator itself can operate in different operating points, and the standards clearly mention that if the generator is at no load and a short circuit happens, you have to simulate that case without any external fault resistance, but you have to consider the arc voltage of the circuit breaker. When it comes to the fact that the generator is already in service, like in, I don't know, overexciting, underexcited, lagging and leading operating points, then you have to consider, of course, the arc voltage of the circuit breaker itself. And additionally, you have to consider also the the arc fault with a minimum arc fault of 300 volts. In real case, it depends on where the short circuit location will happen, whether this is in, let's say, in oil or in air, and what are the distances of the bushing. You can define a different level of arc fault for your case. However, we try to stick to the standard to simulate the worst case, so we use the 300 volt as recommended. Then additionally, you know that we have in the application itself there is a phase shifting between voltage and current, so that does have an effect on the short circuit current itself at the end. So therefore, we always simulate the short circuit current in two different times, I would say. First of all, we simulate that at the voltage 0. That you can see in the upper part of this diagram. So we have the same set of machines and network, only that the short circuit initiation is a different time. And you can see that when the short circuit happens at the voltage 0, you would have a maximum peak current, which is here. So you have a maximum offset when that happens. And by simulating that, you can see what is the maximum offset of the system, what is the maximum peak. And the maximum peak current, of course, means the maximum mechanical stress for the contact system and for the whole system. And then the second case, what we simulate, or we always simulate because it's required by the standards, is that if the short circuit happens at the voltage maximum, that's in the lower part of this diagram, you can see. If that happens, we can see that one phase, which is indicated here as phase R, we have 0 offset. And if that happens, and this phase is cleared first, you can see that the other 2 remaining phases will have the maximum DC offset. And by doing so, we intentionally simulate this case. You can see that the arcing time in that case is higher than in the upper case. So by simulating these 2 cases separately from each other, we can get the first results, maximum mechanical stress for the breaker because of the peak current. And here we can get the maximum arcing time, which is the maximum thermal stress on the contact system. Right. So I just mentioned briefly in the last slide that the arc voltage of the GCB has to be taken into account when simulating interruption or short circuit current. So basically, at the instance of the at the instance of the opening of the circuit breaker, any sorts, you always have an arc initiation. So by doing that, you can see that in the equation which is written here, that the decaying of the short circuit current itself is influenced by the reactance of the system and of course of the resistance. And by having an arc voltage, you have increased the resistance or the resistive component of the circuit. And as you can see here in my lower diagram right now, the dotted line is how it normally looks like without any opening and interruption. And the solid line is what it looks like when you have an effect of an arc inside in this equation. I do want to emphasize the fact that there is some misleading information about that vacuum circuit breaker in general doesn't have any effect, or let's say doesn't have, or the arc inside the vacuum generator circuit breaker doesn't have an effect, which is actually proven wrong. Vacuum switching technology does have quite small value in comparison to SSX or OI generator circuit breaker, but it does have an effect on reducing the arcing time, which we can see here. So it is a real case and real simulation we have done, and as a project, I'd say, delivered. And as you can see that in the lower part of the simulation of the same set, you do not consider any arc voltage here. And of course, that is the normal simulation, what let's say any consultant can do. But we are the manufacturer of the GCB, of the vacuum GCB, so we have the internal knowledge about the characteristic of the vacuum arc, and we have to implement that as requested by the standard to provide our customer with the new simulation, including the effect of an arc of the GCB. And as you can actually see that I do not count how many periods it will be in the lower diagram, but we do, but the arc in the vacuum does have an effect to reducing the arcing time. And that is what we have to do, and that's what we provide to our customer to prove that using vacuum, or let's say the vacuum generator circuit breaker is suitable for generator application in general. And of course, the same is what we are doing with GCB, with generator applications. We do that with the synchronous condenser application as well. All right, so that was a general input about simulations. I would like to go into the operation of generators in general, and of course an except of that will be how synchronous condenser is operating. So with the machines manufactured, there are existing different kind of capability curve depending on the design, depending on the build and type of the machine itself. So you know that the stator with its major current set a certain limitation of the capability curve, and of course with the field winding or the field current excitation, you can set another limit for working of the generator itself. So based on all this information, you would have a capability curve, of course given by your machine manufacturer, which define the working zone or the operating area of a synchronous machine, either condenser or generator. So by doing that, based on that, we can use this information and see how much we can incorporate that in our simulation. What we can see in general is that if the field current, excitation current is larger than 100%, then we are talking about the machine delivering reactive power into the grid or into the network or whatever is connected to. And in such a case, we might have a higher short circuit current at the end. And on the other hand side, if you have an under excitation mode, like if the excitation current is less than 100%, then you are consuming the reactive power from the grid, and therefore in such a case the short circuit current, the amplitude, will be smaller. And how does it look like, and what is the reason behind that? You can see that in this phasor diagram I'm trying to draw. Every machine, every rotating machine can either work in motor mode or in generator mode. And for the synchronous machine, you have of course the terminal voltage, which is like where the GCB, for example, is connected to. But the driving, let's say the driving voltage for the short circuit current is the internal induced voltage. And the amplitude or the value of this internal voltage, it depending on which operating mode the generator is working. And by using this phasor diagram, you can see that in under-excited mode, the internal voltage UP right here is smaller than the terminal voltage. And on the other hand side, if you're working in the overexcited mode, then the internal induced voltage will be larger. And that is the reason, because this voltage is the driving voltage for the short circuit current. And this is why you have higher current amplitudes in overexcitation and lower short circuit current values when working under excitation. Another point with what we have found out is here's a direct comparison in the capability curve of a synchronous generator in the upper hand side. Is the blue diagram, and in the lower diagram you can see the capability curve of the synchronous condenser. Both of them are in the similar range of power. You can see that the synchronous condenser does cover a higher range of reactive power, and I mean that's what the machine is used for, because we want to provide, of course, on one hand the short circuit power to the grid, but on the other hand we want to regulate the power factor in the grid. So that's why our aim is, or the aim of using synchronous condenser is sometimes just to provide reactive power, and I want to go as much as possible into 0.1 power factor. So that's like the main working capability, operating area of a synchronous condenser. And in the direct comparison, of course, you can see that generator itself covers only the smaller range of the capability curve, because they tend to use in the rated operating points to provide reactive and active power. But for regulation, of course, you go into the edge of the machine, and so that's why synchronous condenser covers more or less the limits of the machine. As already mentioned before, when doing direct comparison of the short circuit current or short circuit behavior, we have found out that the operating point does have an influence on the short circuit current value and the short circuit current behavior, we always see that the lagging power factor or overexcitation shows higher short circuit current. So that means the breaking current is of course higher, and of course the peak current itself is of course also higher. However, on the other hand, the leading power factor delivers the highest asymmetry, because you've seen before the current value itself reduces while the DC component in the system still remains the same. So in direct comparison, you would see a higher offset in case of leading power factor or in underexcitation, which is all explained in this, let's say, simplification of phasor diagram. Well, we just spoke about the general input and how much the operating points influences the short circuit current behavior. One of the main jobs, as I mentioned before, is the synchronization of the generator and the grid. So what happens to the system if we have a false synchronization? And there's a term induced in the standard which is called the out of phase switching duty. That means we intentionally test the case where the synchronization is not in phase. As it has been found out that the amplitude of the out of phase voltage, of course, depending on the out of phase angle. You can have generator and system in phase, that means the out of phase angle would be 0. Or you can have the out of phase angle of 90 degrees, which is written in the standard and you have to test it for. Or you can have the phase that the out of phase angle is 180 degrees, which is like the maximum opposition what can happen. And as you can see in this little diagram on the left hand side, I hope I can show that here, you can see that there's a influence of the out of phase angle and the amplitude of the voltage, and the out of phase voltage of course will determine how much the out of phase current will be. As you can see here in my two diagrams with the direct comparison, so it's the same set of machines, same set of system network. You have seen before the current constriction we have talked about. And we can clearly see that with the out of phase of only 90 degrees, smaller out of phase angle, you would have smaller fault current, of course, because the driving voltage is now smaller. However, on the other hand side, you can see that with the same system, we have at 180 degrees out of phase angle, the current constriction is now happening later. So the factor which, let's say, influences or dictates this behavior is largely in the machine parameters, time constants, reactances. Another point is because we are talking about full synchronization of generator and the grid. So that's why the grid data is also very important to get this kind of information. The reason, therefore, we will see that in the next two slides. And lastly, one very important, let's say, parameter which dictates this behavior is the inertia of the machine. The inertia of the machine, let's say, gives the system how fast or how slow the machine will, or let's say the whole system will interact in case of such kind of transient process. So generally speaking, if you have a smaller inertia, your system will react slower than if you have a, no, sorry, I'm mistaking that. If you have small inertia, then the system will react faster. Example, as in 90 degrees. If you have larger inertia, then your system will react slower, which can be seen, for example, here. The constriction will happen later. Concrete example, I will show you that in the next slide. So we talked about the reactances. So what we have found out is that the machine parameter between synchronous generator, conventional synchronous generator, and synchronous condenser does not have much differences. So relation are quite similar, the time constant are quite similar to that. The only difference they have here in this parameter is that the synchronous condenser of the same, let's say, power has very small reactances. So that's why if we have the same set of, let's say, the same apparent power of synchronous generator or synchronous condenser, the condenser always gives a higher short circuit current level than a generator. So it might be that if you are, I don't know, asking for a solution, you say this is the same as a machine of the same power, but using a two different function, then it might be that for a synchronous condenser, a higher short circuit current rating might be required. Another point I have mentioned is the inertia of the system. So the synchronous generator itself, of course, you usually connected to a turbine and delivering that inertia of the system, what we need for the simulation. The synchronous condenser might not be connected to a turbine, but it can be connected to a flywheel to increase the inertia of the rotor stuff. So the value itself is, we cannot predict that. We have a data bank which can, let's say, assume a direction, how much I can assume for my simulation. However, to be sure, we might need the real data sheet to exactly simulate the case. And why is it so important to have these kind of information I will show you right now in the feasibility study we have. So you've seen 3 different simulations here. It is of the reapplication we have seen. We have, from one of our cases we have delivered. So the data is from the generator and from the transformer is coming from data sheets we have received from our customer, from our clients. So in this diagram, you can see that is the simulation have been done with the given information, like given data from the data sheet. So our focus right now is on the inertia. And what have been done is we have reduced the inertia from the data sheet now by 50%. And as you remember, I told you by reducing the inertia, so with smaller inertia, that means the system will react earlier or faster on changes, on transient processes. So you can see that now the current constriction is now here, and after we reducing the inertia, we have moved this current constriction to the front. And the same set of machine, same set of data is now being used to simulate that case. But right now, we increase this inertia by 50%. And right now, you can see that the constriction is now moving to a later point of time. What does it mean for the circuit breaker itself? Now we have simulated that in cooperation with the arc voltage of the circuit breaker. You can see that the arcing time right now, you remember the case I mentioned with the voltage maximum to generate the maximum arcing time. So standard case have been simulated here, and of course that has been always these values you can see here is tested for our product, and you can see that for such a case, even though we have the construction now earlier, but you can open that always earlier, so that means the arcing time now can be smaller as well. And right now, if I would go back, you can see the curve that's even the constriction is later, but we are opening right now here, and at the point of the contact separation of the breaker, there is no constriction at all. So that's why it doesn't have any effect on the breaker. So you can see that same set of system data, depending on which data is being used and how much the modification has been done, we get 3 different results. So a generic question, let's say statement about vacuum not being suitable to use for out-of-phase case or synchronous condenser is not true. So that's why, but still we need your input. I need a complete set of data and all the information I need to exactly simulate these kind of cases, because you see that by modifying one of the facts, let's say one of the factor, we get different results as well. So inertia is only one part or one factor which determines the behavior in case of out of phase. Another point of what I mentioned is because we have an interaction between generator and the system. So the system data are always also crucial to have. So you remember, my green diagram is how it looks like with the real given data. And what we can do is we can change the input data, like the grid X2R ratio, the transformer X2R ratio. Of course, the short circuit capability from the grid does have an influence here right now, and of course the high voltage level. So all of that facts have been implemented, and as you can see that by changing one of the factor, we can have either negative or positive results. It's very it's a large number of variants which we can get. So I can only emphasize, please, if you want to have an, let's say, recommendation, a solid recommendation, we need the solid input to get any recommendation out of that. All right, so actually I've been at the end of my presentation already. So what I want to give you, the audience, for today is feasibility study have been made, and this is required to confirm the suitability of our VGCB for synchronous application. You have seen that short circuit current calculation have been included, and of course for the out of phase case, we have seen that synchronous condenser have a lower reactances, so it's often that the short circuit current level is higher. Also, the operating points itself of the machine does have an effect on the short circuit current level. Either you have higher current or you have higher asymmetry, depending on which operating points we are working with. You have seen also that the fault current, due to fault synchronization, depending on the input data, might have very critical or not critical results at all. So it's very depending, or strongly depending on the input data. And of course, we have seen with our studies with different set of machines and system that the impact of inertia is quite significant for the interaction between the generator and the system. So that is what I can give to you. In case of any question for later or more details consulting, just reach me after the session.